So there is a small deviations. I am supposed now at the moment to start power amplifier, but what I said that I got the feedback from most during my yesterday night's banquet dinner, and now there many students are interested to learn a little bit of layout, and which is not normally available in any textbook or references. So that's why I think that let me spend some time in layout using standard cadence platform, and we'll be using 65 or 180?
65.
We are using 65 nanometer technology node for just to show how a schematic, transform the schematic to the layout, then post layout, then simulation of that, how it differs, all those intricate issues in the VLSI design. And maybe after that, I will go into the power amplifier. So is it okay? Fine? Should the layout? Okay. And I will be assisted by my student, and who happens to be one student who is dedicated for layout. He is working for last 2.5 years to designing a very, very complicated circuits for an European Union projects. At a very complicated design, 5 gigahertz, 5 gigabit per second serializer, deserializer at 65. So he is really experienced in that way. So probably you can learn a lot regarding the VLSI layout for analog and RF design. Okay, start.
Thank you, sir. Once again, welcome to all. So now I am going to tell some basics about layout, that is RF, analog and RF layout. So after that, I will show some schematic versus layout simulation, post layout simulations, and I will tell some techniques what I have experienced last 2 years. Generally, you will not get these things in any theory or any books. So this is experience things. So that thing I will share. So first, this is the introduction. Then I will tell the basics of analog and RF. Actually, analog part is somewhat it is easier than RF. RF is most complicated. So first, if you will do an analog layout, then definitely you can do RF layout. Without analog, you cannot go RF layout. It's very difficult. Next thing, some constants are there, means geometry constants. That is length, width, spacing, lot of things are there. I will discuss. Next thing, some issues. What are the issues, main issues in the analog and RF layout? That thing I will clearly explain. Then, what are the technique? What are the technique we will use to minimize the parasitics, for matching, for symmetry? Lot of things are there. So that thing we will discuss. Next, I will discuss about how to do the layout of active devices like MOSFETs, BJT, diodes, and MOS caps also. And next thing, passive devices like capacitors, resistors, and inductors. Okay. Then I will give some brief idea about how to do floor plan, placement, and routing. Then after that, a complete system level layout design. How to do the complete system level layout. Very basic things I will tell, but after that, if you will know this, then you can proceed. This is the main. So first, what is layout? Layout nothing but the geometrical representation of mask which will be fabricated. That is it is a multi-layer drawing of active devices, passive devices, and interconnection of that. Otherwise, we can say, if you will see the top view of a chip, you will see the top view of chip which satisfies the design rules, spacing rules, and minimum length, minimum width, and enclosure, dummy, lot of things are there. So that thing should be satisfied. Otherwise, we cannot say that layout is a perfect layout. Layout basically gives the information about the length of the devices, total width of the devices, the number of fingers and finger width. Next, orientation of the device, because orientation is important. You cannot put randomly. So you have putting transistor means always transistor, all blocks, everything should be in one orientation, means either vertical or horizontally. Otherwise, performance will be degraded. Next thing is spacing between the devices and metal layers. That is more important, because if you will put metal layers side by side, then more parasitics will come. And also if you will use lower metals, then substrate capacitance will come. So you have to choose judiciously the metal layers. For example, for signal layers, you will choose the middle level layers. Means suppose for example TSMC 6590, it is a 6Z1U1Z process, 6X1Z1U process. Means total 9 layer metals, metal one is first level, then 6X 2 to 7 is 6S, and 8 metal number is 1Z, and 9 metal level is 1U, means ultra thick. Okay. So you have to choose for signal routing, that is 5 and 6 number metal. It's a middle, means for 9 and 8 you will use for power routing, because its width is more. Generally in 65 nanometer, the width, the thickness of the metal 1 is around 900 angstrom, metal 2 to metal 7 is 2200 angstrom, metal 8 is 9000 angstrom, and metal 9 is 34,000 angstrom. So the thickness is more, so resistance also less. So generally we are using metal 9, metal 8 for power routing, and metals 5, 6 for signal routing, and for control lines generally metal 2, metal 3, like that. Also biasing purpose we are using metal 2, metal 3, but we are using proper shielding, otherwise it will create some problem, because for CML design biasing circuit, biasing is very important. If any noise enter to the biasing path, then it will create a problem. So in biasing in metal 2, generally lower metal levels we are using for block level routing, and upper metal system level routing, and middle level is for signal routing, for clock or input output signal, like that. Yeah, it's analog or RF layout is completely different from digital layout, because digital layout generally we are not doing anything, its tool is doing everything, but analog RF is a customized. So we have to do everything, we have to do from a inverter to from system level, we have to do everything. For routing, we choosing the metal layers, and orthogonality, dummy, spacing, shielding, everything we have to do. So that's a very difficult task. And in digital only we are considering the speed, but here speed, precision, noise, everything is there. So you have to choose judiciously the metal layers, the placement of the blocks, and DC blocks, and the main core blocks, and digital. If digital part is there inside the system, put some distance between digital and analog, and make some analog VDD, digital VDD. For digital use digital VDD, for analog part use analog VDD. So you have to choose that way. That's why it's difficult. And next thing is, if you will calculate, suppose your total time required for schematic to layout, suppose 100%, minimum you have to give around 50 to 60% in layout, otherwise it is not possible. Because from that 60% you have to think how to do, how to place the blocks. Means it should be actually in industry people are fighting for one femto, that is very important. In high speed design, that means 5 gigahertz or 10 gigahertz, it's very difficult. Even if one femtofarad kill your circuit, that's it's very difficult and very important. So that's why you have to think properly how I will make the design, then it will simultaneously the distance between input to output will be less, and it will create less capacity, less parasitics, and less inductance. Suppose the metal length will be more, inductance will come. That if you want parasitic capacitance will come across that resonator, it will create some oscillations. Okay. So extra parasitics will come, resistance and parasitics, extra pole and zeros will coming to the circuit performance will degrade. For high speed operation, sometimes what happen, ISI problem will come, because in rectangular or square wave pulse, it contains higher order harmonics, means higher frequency components. So RC parasitics will come, will it act as a low pass filter. So that higher frequency component will not pass. That's why it will something, it will interfere with the adjacent symbols. That is coming in IC. That is we are saying that ISI problems. Inter-symbol interference. Generally, it is degrades the bit error performance of the circuit, whole system. This is the general constants, you know, the design rules, that minimum width, minimum length, that should be fixed. You cannot go, then minimum spacing also, minimum enclosure, lot of enclosures are there, VTLP, VTLN, then NOL, dummy, metal, DM, for blocking you have to use some enclosure, lot of enclosures are there. So that is fixed, you cannot go beyond that. And the design, and next is, these are the 4 important rules. DRC, design rule check, you know. ERC, electrical rule check, whether the circuit is short or open, means that VDD or ground is short or open, that thing you can know from ERC. Then layout versus schematic. After doing layout, you will check the net list of the schematic and net list of the layout. You will compare whether it is correct, you will give this correct, otherwise even you will go again for checking. Next, layout parasitic extraction. Generally, we are saying it is specs, parasitic extraction. In this, you will extract the parasitic, the node parasitics. Then you will finally check the schematic versus post layout simulation by using the PEX information. These are the issues. Already I have said some issues. The parasitic resistance or parasitic capacitance, the rise and unintended pole and zeros, and inter-symbol interference. And main thing is parasitic resistance will create thermal noise. It's more important. So unnecessary, the circuit performance will be degraded. And long interconnect of the parasitic inductor also creates a LC resonator because it creates as a inductor. Okay. And parallel placement of interconnect raise a crosstalk of signals. Okay. Suppose one line is going, besides another line is going. Suppose one line signal level is suppose 0.5 volt, another signal level is 0.7, 0.8, whatever may be, and frequency may be different. So that will couple to side by side line. It will create crosstalk. And asymmetric placement of interconnection creates skew in digital and phase lag in analog. So the circuit should be always symmetric. Means suppose differential circuit, the output always symmetric, or input also symmetric. Means that should not be any skew or any phase lag of the differential inputs. Okay. And another thing is, suppose any floating metal is there, ground or any metal, it will act as a antenna, it will radiate signals, it will affect the side wave blocks. Some technicals. These are the main techniques. So this is very basic theory, but practical is somewhat different. I will show you in design. So use multi-finger transistor. Generally, it's a very important the ratio. Suppose your transistor is very long, means 100 micrometer length W, but 60 nanometer your length. You cannot put a transistor with 100 micrometer W and 60 nanometer length. The rule is the ratio should be 10, means W to L is equal to 10. That's why you have to put 16 to 10, that is 600 nanometer maximum, the W. That's why you have to go for multi-finger transistor. Okay. And yes, I will show you.
But how it reduce the parasitic capacitance?
See. This is source and drain. This is suppose width. So when you will go for multi-finger, suppose make it 3 finger. So for this transistor, C SD and C source to bulk and C drain to bulk is the capacitor. See, this is W by 3. This is W, but this transistor is W by 3. So source to this is source, 2 source is here and 2 drain is there, and total capacitance is 2 by 3 CSB and CDB also 2 by 3 CDB. Is it possible or not? Why? No, capacitor is depends on the W. Okay. Now W reduced to 1 by 3. So capacitance also reduced to 1 by 3. See,
Addition of all W.
this is 2 source and 2 drain. Here 1 source, 1 drain. Here W is here W, but here W by 3.
W of the multi-finger transistor will be the addition of all W.
Yes.
Yes, so capacitance will not decrease. I haven't seen any reference for that. Only resistance decreases by 1 by 12 n square.
1 by 4.
1 by
1 by 4
12.
times resistance will
1 by
increase.
12 if you connect from both sides in the layout, and 1 by 3 in the if you connect from one side.
No, resistor will decrease 1 by the dividend factor. Means it's 3 divided means 1 by 9 times resistance will be decreased.
No, it is
Why?
1/3 n square and 1/12 n square. You see the references in IEEE journals.
See, this is the gate resistance. Now W.
No, this number 1 by 3 n square and 1 by 12 n square is obtained through fitting.
Actually, can
Through
we
fitting.
discuss in offline?
Yes, sir. I will
Because the
discuss
flow
later.
is-
See this figure. PPT. See this figure. For W, the single transistor, that source to bulk and drain to bulk is the capacitance. Now W changes to W by 2, 2 fingers. Here 2 drain is there, 1 source is there. That's why capacitance drain to bulk is same, but source to bulk is half because 1 source. Here 2 source and 2 drain. Again CSB 2 by 3 CSB and CDB is equal to 2 by 3 C cap dB. You can consult with your friend.
Yeah, please. I think that let us. Yeah, come on.
So the 2 drains are connected as a single drain. So actually the capacitance will be reduced. If you are using a single long transistor, then you will be taking the total width as the drain capacitance for source capacitance. Now,
Exactly.
Take up this because
yeah.
if I can start work please learn it.
Okay. So these are the techniques. Use multi-finger transistors. It is definitely you will get less resistance and less capacitance also. Use interdigital transistor to reduce effect of process related issues, offsets, temperature gradients and process variations. Okay. Compensator is very important for low frequency and DC.
Go to design and
Okay.
explain this. Go to design and
This is some interdigitated device. So don't make a transistor means very high W. So make it short and make it lot of fingers. For this, what you will get benefit? You will get some reduced process variation and placement wise it will be fit to your blocks. That is very important. Otherwise, if you will make one transistor very lengthy, it will be problematic for other blocks. And this is some general rules how to integrate devices. Suppose one transistor is A or two transistors are there. So you can make AA or ABBA, ABCCA like that. Okay. This is two transistors. Suppose okay, suppose this is two transistors, transistor A and transistor B. Suppose it is 4 finger, this is also 4 finger. So make it total 8 finger. Okay. So make it one transistor, this is 8 finger. Okay. So now it is total 8 finger. So make it like this way, means this should be, suppose this is A and this is A, this is B, this is B, this is A, this is A, this is B, this is B. See, B, 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 this is 4 transistor and A, this is 4 transistor. So how you will get benefit if you will make this? See, the process variance, the silicon is a anisotropic material, means there is the everywhere it's not uniform, the doping profile is not uniform, so it may vary in this way.
Just to give you a bird's eye view about this process variation, how it is important. Just 2 years back, I designed something on 6-inch wafer in a process foundry, and I asked them to give me the sheet resistance profile of that wafer. And I found there is 10 to 12% variations in the sheet resistance, just throughout the wafer in a 6-inch. Now think of one transistor which is at the center of the wafer and another transistor is at the edge of it. Then you will have mu and Cox W by L. So mu, your intrinsic parameter gets changed because of the doping. It is unimplanted and is doped with, say, 3-zone doping by unimplantations. So you have doped with effluence of something, so that which one having higher sheet resistance, ab initio, when it is doped with something, then to compensate it, the same doping concentrations. So there is a huge difference in these effective carrier concentrations. That's why the mobility, the mu, n, everything, there is a variations in this. So I found 10 to 12% variations in the GM itself. Okay. And then we asked the foundry that you go for a different, you give me some another wafer where you will have a better sheet resistance profile. Yeah, ab initio, I'm not talking about just freshly cut silicon 6-inch wafer. By inquisitiveness, I made the sheet resistance measurement, kept giving a surface profile of that. So it gives me color band. The green one will be the lowest resistance and the red one is the highest resistance. So believe it or not, hold the wafer, I found this green and the red patches. That means variation of resistance, sheet resistance. Then you doping, so immediately the doping will not the same effect, which is have a higher sheet resistance than others. And so in a differential structure, what I said that you try to imbibe that changes yourself. Please make any design when it is perfect, say all the GM, W by L of the differential pair are the same. Okay, and you are calculating everything fine, but then introduced at least 10% mismatch in your GM and see your circuit still working or not. That is the thumb rule. 10% mismatch you can generate by 2 ways. One, by increasing the resistance, so current will be less, so GM will be reduced, or you can actually make by changing the W by L. Sometime the changing W by L will affect other device parameters. So better you straightway change the resistance and accordingly change the GM. So take that 10% mismatch in your GM and then you clarify your isolation, your harmonic content and so on. So here in this schematic, when you go for the layout, that GM variations is important. make it say 1 to 2% variations is often found in any design. Come on.
See how the gradient is compensated here. So this is the total 2 transistors, make it 1 transistor, 8 fingers. So simply you put 1, 2, 3, 4, 5, 6, 7, 8 and just add, means A. So 1, 3, 6, 8, 8, 6, 14, 3, 17, 18. Total A is equal to 18. Here same way, same B. 2, 4, 5, 9 to 11, then 8. Sorry, 7. B is equal to 18. So it is perfectly matched. Similarly, go to slide. Similarly, you will check everywhere you will get perfectly matched. The number of A is equal to number of B. This is the interdigitization technique. Next, orientation of the device. So it is generally advisable to make all the transistor, all the blocks, all the passive and active devices in a single orientation. Don't make different randomly, one is vertically, one is horizontally. It's not a problem, but generally advisable. And next is common centroid. Common centroid is the most important matching technique in DC or low frequency circuits. Okay, and don't try it for a high frequency circuit. Unnecessary, it will create some routing issues, because if you will make common centroid in RF or high frequency circuits, then you will get matching in DC level, but due to some number of routings, extra parasitics will come, that is will also degrade your performance.
So common centroid architecture which you have picked for analog design sometimes look to be very fancy, but in RF design you take care of about the routing, the total path. If the path length increases, interconnects path length, that would introduce unnecessary those parasitics to keep it in a centroid format. So then you have to make little bit of compromise. Okay, so that's what is mentioning. Come on.
This is some formats of common centroid. Suppose one long width of the transistor which width is more, so you can make it 2 transistors. Suppose 1 transistor, so you can make it 4 transistor also. Two row and 2 column. Okay, so make it A, B, A like that. Suppose 2 transistors are there, A, B, you can make it like this, that way. A, B, B, A is 1, 2, 1, 2. So add 1, 2 is 3, 1. Yeah, 1 and this 2, 3. Everywhere you will get matching. So this is the main. You can make it 3 rows, 4 rows. Okay, but you have to calculate all the rows and all the columns, whether its number is matching or not. So you can make some innovative also. Only thing is you have to check whether numbers are matching or not. If numbers are matching, then it's perfectly matched, no problem will come. And dummy device is also very important in differential circuits and low frequency circuits. In high frequency circuits also it creates some parasitic effects, but it's important because if you will go to lower technology, and so it will create some boundary effects, means the transistor property at boundary and internal it's different. That's why you have to put at the boundary some dummy metals. Okay, that's why it will not create any problem. And in passive devices also, resistors and capacitors, we will put some dummies.
Actually, for metallization, there is a design rule that say 75% should be your total metal on the layout. That is given by the foundry. So if you do not have, say, your total metallization within, say, 55% or 65%, then you will say your DRC fail. That means the 75% rule for metallization is not obeyed, then what you have to do? You have to actually make some additional metallization at the layout level that will add to your actual layout and make it more than 75%. Then you will find that your design rule check is validated. So you may not be knowing, you may not be using that metal layers, but just to satisfy the DRC, you have to add those additional. These are the tricks I am giving you. So that is called the dummy. So you make some dummy to satisfy your design rule. Okay.
Here is one example is that stack how to make stack layout. So it is a basic two-stage OTA. So here how to make the transistors how to make the transistor fingers properly that it will not create any problem. See here M1 and M2 are signal transistors, means it will, and M5 and M7 is like biasing transistors, and M3, M4 and M6 it's same type of transistors.
Where is this? You can show it by this. You can show it.
Sorry. So here, yeah, this is M3, M4. Generally, you know the basic OTA. So M3, M4, and M6 are all P-type transistors. Okay, you will put it in N-well, and M1, M2 are N-type transistors. Okay, so it is the same type signal transistor. It should be matched, and M5 and say M7 are biasing transistors. So that's why its length also same, and according to that width set. So that's why you make it 3 stacks, M3, M4 and M6 in one stack. Next stack is M1 and M2 and M5 and M7 below of that. So see here M3, M4 contains 30, 30, 60, 60 and M6 108. Total 60 plus 108, 168 fingers. Here 60, 60, 120 fingers. Here 40 and 72, 112 fingers. Yeah. So just make 108 and 72 with multiply some ratio which will make 120 and it is 80. Then you will get total 60 plus 60 is equal to 120 M1 and M2, and here M1 and 7 40 plus 80 120, and here 30 plus 30 plus 120 is 180. So after layout you will see the block is perfectly square type. So everywhere it's not any process variation. That's why you have to do that way. You have to make stack and some adjustment of fingers. That's why you will get perfect layout which will match, which will put, which will fit to your systems.
So basically, two important aspects. One is the variation of the oxide thickness or variation of its doping parameter, which introduces the changes in the transistors, and that is special variations because of this. Now you are planning your float such a way that either these deviations will be cancelled. So someone is increased, someone has decreased. So you should not add them together, then the difference will be high. So you should make in such a way that their difference gets reduced. That is the whole philosophy of the floor plan. So you are making, suppose gradient is, all of you know the oxide thickness, when you do the plasma processing, the middle of the wafer, the thickness will be high, and at the edge, the thickness is less. So look at the oxide capacitance. The capacitance will be high at the fringe or the edge of the wafer, and capacitance will be low at the center of the wafer. Now look at the threshold voltage. Threshold voltage depending upon that, the oxide thickness, because that is finally depending upon your barrier potential and so on. So now you can plan, okay, I can make a balance. I will take some transistor to the one side of the center points and some transistor to the other side of this, and then I will compensate that one. So this way, that is called the squaring. So they are using this one. So once you know the actual reason of doing this, then it will be much more easier rather than going into those 1, 2, 3, 4, 5, 6 like this. So try to understand philosophically that what is going on actually inside the chip. You are placing the transistor in such a way that while they are interconnected, they are intercompensating each other's deviations to give a uniform value. Clear? So that's the meaning of the meaningful routing and placement. Come on.
Next is the basic cell design. Actually, first the layout is not a bottom-up approach. It is all a top-down approach. That means first you have to think about the total area. After that you think about the blocks. Then blocks means your cells. Then you will design your cell within that space. That is very important. So for cell design, first you have to draw a well-readable transistor diagram. Then identify the critical elements and nodes. Which path is critical, means high frequency path, or some nodes which suppose parasitics will add, it will create some degradation performance. So you have to identify the paths and the nodes. Then mark that transistor must match. Suppose one current mirror is there, you have to identify which part should be matched. Then mark symmetry axes. For differential circuits, you have to make some arrangement for symmetry. Then change transistor size for layout oriented strategy.
Go to design.
Yeah, group. These are the main points. You can go through this. Okay, these are the main points you have to follow. Otherwise,
Go to design.
okay. Here are some passive devices, layout of capacitors. To achieve good matching, use unit capacitors connected in parallel. Suppose one big capacitor is there and small capacitor is there. Suppose in VCO design, so you have to, for variable frequency, you have to put some capacitance. That is 5-bit tuning capacitance. Suppose one capacitor is 1 femto, another 2 femto, 4, 8, 16 like that. So 16 compared to 1 femto, 16 is very high. So make it 1 femto for all capacitance, means 16 plus 8 plus 4 plus 2 plus 1. Total make it 32 1 femtofarad capacitors. Then make a arrangement that it all should be matched. In that way you have to put the minimum capacitance size. Next, use dummy capacitance also, and use shielding. Shielding I will say differently, but just here I will not discuss, but for shielding means how to shield the bisingle path, how to shield the frequency path.
Few do's and done. So you don't run, say, interconnects over a capacitor. Place the capacitors far from the power devices. So these are few observations you should be careful, because this instruction will be with you in your I think in the slides given to you. So while you will be designing, make sure that you have taken into account. This is a summary sheet of what you should do and what you should not do that. Let's go to the design.
One capacitor, here C1, C2, C3, C4, C5, 5 capacitance are there. C2 is equal to C1, C3 2C1, C4 to 4C1 and C5 8C1. Its total is 12, 14, 15 C1. If you calculate, it's 15 C1. So here make total 16 capacitance of C1 value and connect accordingly. See, this capacitance connection is 1, 2, 3, 4, 5, 6, 7, 8. Okay, this is C5 and this is 1, 2, 3 and 4. This is C4 and this is 1, 2. This is C3 and this is C1. Okay. So in this way you have to put, otherwise matching will not come.
So you understand that, as I mentioned, your thickness of the oxide is varying. So suppose I want to make an 8 picofarad capacitor and I put one single capacitor there, another 2 picofarad, maybe their oxide cap difference introduces at least 20 to 30% changes in my capacitance. So all your circuit will go haywire. So then you are using basically single unit capacitors. Then you connected those capacitors in parallel, such a way you can have all those values which you require. That's why if you look at the layout, is a huge patch which is actually designated as the capacitors. Not as a single block, isolated block like inductor, here, 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 something like this. It's a patch, squarish patch, where all the interconnected capacitors provides you the required capacitor. So you can have the less variation of the capacitance. Come on.
This way your area will be no area will be wasted, and it's a cement means square format. So resistors also you can make, suppose resistors whose value is very high. So this is two resistance. Yes. See, this is two resistance R1 and R2. So if we will put side by side, this is one resistor and this is one resistor. Again the variation will come for this one value, for this one value. So make it in this way that it is one interdigitated type. Make it some 4 to 5 transistors, resistors, make it also 4 to 5 resistors and put inside that, like this way. This is one resistor. This is R1, again R2.
So clear? So in spite of this huge resistance, you make those unit resistance and then you interconnect and make the total resistance is the same.
Put that number 1, 2, 3, 4, 5, 6, then R, definitely R1 equal to R2. That means it's matching. And it's also generally said snake resistor. Suppose one resistor value is very high, you can for area constant you have to make this way.
Another kind of structure, so that area is optimized in that way.
This is floor plan placement and routing. So this is actually first step. Before going to layout, so first you have to think about how much is the area. Means it's a costly process. Randomly you cannot use that much area, this much area. So you have to restrict about the area. So first you think, yes. So list the active cells, then area estimation. Interconnection and biasing area is 50%. That means BGR and the interconnects of that power line to all blocks. It's approximately 50%. Then accuracy and shielding needs, matching of resistors and capacitors. Then placement of active cells is important because power blocks are there, high frequency blocks are there. So you have to make arrangement also, means high frequency block and power block should be more distance. And placement of passive components also, mainly capacitance also placed side, not side by any high frequency component or power blocks. And placement of switch, if any, routing of signal lines with proper shieldings. So here I'll it's a very important thing, how to shield the power lines and how to shield the clock lines, I will say. This is suppose BGR, this is BGR. So here your PLL is there, suppose CDR is your serializer. So
PLL is the phase lock loop and there is a clock data recovery circuit. The mixed signal floor plan. So how the band gap reference will be routed? So explain.
So this is for PLL, one line will go, for BGR one line will go power, again for CDR one line will go. So it may cover lot of distance. So what happen, suppose any noise will come into this line, then it will create some problem in sensitive blocks like PLL and CDR. So that's why what we will do, we will do some 3D shielding. What is 3D shielding? Means generally we use metal 1, metal 2, metal 3 for 3D shielding in power routing. So what we will do, the connection should be in metal 2 and make some metal, mean metal 1 below that metal 2 and metal 3 over that metal 2. This is one type of shielding. Means this is metal 2 and here metal 3 is metal 1, is metal 1, is metal 3, is metal 2. metal through actually connected through the BGR. So power will go this metal to. So from upper side or lower side, substrate effect and upper from upper blocks, upper metal, no noise will come. And these two, metal 1 and metal 3 will be ground.
Clear? Very simple. So you have the power line and you are shielding it in a 3D way. So the immediately top metal layer and the immediately lower bottom layer are actually using as the guard layer, and that should be connected common and then putting to the ground.
No.
So this will be shielded. Clear? Next one.
This is actually, this is one type of shielding. But what is 3D shielding? Side by side also you can put shielding. Means here metal 2, this is metal 2, suppose this is metal 2, this is metal 1, this is metal 3. Here we can put metal 2, here we can put metal 2. Then from everywhere is shielding. No noise will come from top, bottom, side also. Okay. That is the main 3D shielding in we.
Do that, this sidewise TSB. Do metal 1, metal, suppose metal 2 your line, metal 3 in the top and metal 1 is that. So metal 1 to metal 3 you need through silicon vias.
Actually that
so
thing I will show you in
it is just like
design.
a cage. Yeah. You show it, you have some.
I will show in design, but okay. So finally it is a mixed signal layout. Draw a well readable system diagram. Identify critical blocks and connections, sensitive nodes and critical paths. Marks passive components that must match. Mark symmetry axes.
Go to design.
Yeah.
You can read it. You can read it. Go to the design.
So these are the references we will make. So now I am going to the tool and I will show you the designs.
So the references are given in the text, so you can go through that references. Okay? But it is better you learn the design now. We are giving some. What you are using at the moment?
First BGR I will show.
So we will give you a design of a band gap reference and its layout.
See, this is our BGR. So this is the BGR core, and these circuits are for we are using lot of power options, variable power options. That's why for CDR, for PLL, and for serializer and PRBS, lot of blocks are there. That's why we make lot of options. We can vary also. So now I will show you the layout of the BGR core. So this is the layout of total BGR. See, I have said you have to match the transistors also in this way. See, this is the BJT. You all know the BGR circuit, that one transistor, another side is 8 or 16. You can. So that's why this one is for one path, this 8 for another path. So in this way you will match. This is the main beauty of a BGR. Only this part is important, how to match that BJT. Okay. This is the auxiliary block and this is the main block, and these are the, what I said, the options, means for CDR, for PLL, for we have to make some number of ports. This thing will go to CDR, this thing will go to PLL, because it will create some loading effect. If you don't make, if you put one line to all blocks, then definitely it will not work. So that's why here we have made separate lines for separate blocks. Okay. So I can, this is BGR. Next I will show you VCO. Yeah. So this is VCO schematic. Okay, this is two biasing transistor. Then see one inductor is there. Okay, inductor. And these are the capacitors which will vary your frequency. Okay, these are the switches. Okay, and this is cross coupled transistor. Sorry, this is cross coupled transistor. This and this is vari cap. MOS varactor. So these are the components in the VCO: cross coupled, varicap, switching transistors with capacitor, inductor plus 2 biasing transistor. Now see the layout. The most difficult part means to design a VCO in high frequency. It will work in schematic even if 3.5 ampere or 4 milliampere, 3.5 milliampere or 4 milliampere, but layout you cannot get the result with that current. So you have to think very innovatively how to make the layout of VCO, then it will work after post layout. Just wait. Yeah. This is inductor. And this part is the this part is the variable capacitors, and this is the switches. We are using 4-bit switch. Okay. So this is switch, this is capacitors perfectly symmetrical, and these are the variable capacitor that I have shown you. And this is the cross coupled transistor. This is very nearer to the inductor because the GM is the main part. Oh, sorry. Yeah. See, here the cross coupled transistors are very nearer to the inductor. Why? If any path resistance will come, then GM disturbance will come, means startup will not come, oscillation will not start. That's why to minimize the path resistance, I have put the cross coupled transistors very near to the inductor. Then I here the varicap capacitors, and here the main tuning capacitance, and there is the switching. Is the switch. It's not required that is a digital type things. So you can put it some distance to that inductor or capacitor. It's not PMOS cross coupled is not here. NMOS cross coupled only. And this is the biasing transistors, which will give the current to the inductor. These are the cascaded transistors. It is giving current to the total circuit. It's a huge transistor. Its W is 1440 fingers. 1440 fingers. That is, finger length is around 5 micro. So that's a it's a huge transistor. Yeah. No, 1.2. Threshold voltage around 0.4. Next thing is I can show you.
Any results?
Yeah, just it's going.
Just go to some schematic simulation and then show the post layout simulations.
Yeah, I
Any
already.
such VCO or
Yeah,
anything?
it's
and show
already.
how it differs. Go to the schematic and then the post layout. Yeah. Say VCO. Yeah. Yeah. Show it. But make the color little yellow so that they can see.
Now I am going to show you some VCO result.
Yeah.
Schematic versus post layout
Yeah.
result.
So that is important, that suppose you made the schematic and see the results and then go for post layout, then see what is the difference. Sure.
See, this is our test bench. Here BGR is connected. Okay, BGR layout version also collected, and this is design core VCO 10 gigahertz. This is schematic and this is layout. Okay, now I will show you the result.
It takes time.
It's coming.
So can you just change the color because red is not visible from the back.
It's not started.
So you have some transient and then the oscillation builds up. Yes, sure. That should be within few nanoseconds. Yeah. Okay, so can you just change the color?
Just I am changing.
Can you see from the back side? Yeah, so show it. The file size itself 2 GB. Got it. So it's okay. So this is post layout or
Yeah, yes. Just I'm saying color.
a schematic? Yeah, so which one is schematic and which one is post layout?
Schematic is the showing is more. This is schematic.
Yeah, the schematic is the yellow line,
Yeah.
and this is the post layout, right?
Yeah.
So why this difference?
Different. देखो merge करो.
Background you cannot change. Yeah, it is visible now. It's okay. It is visible. You just go to the explanations. Yeah, so it's fine. Yeah. So look at here. So now explain. Okay, that's done. It is seeing. Just go through this. So look at the transient and explain.
No, ठीक. See here the schematic and this is the post layout. So schematic started earlier. In the post layout it's somewhat delayed. Okay, now see the actually we will see here the swing, mainly the swing of both curves. Yeah. See, this is swing is for schematic. It is 628.9 millivolts. Okay, it's okay. But 600 millivolts is okay. For post layout, it is 625.21. That is 628 and it's 625. It's almost same. The swing is 628 for schematic and 625 for layout, post layout. 10 gigahertz.
It is 10 gigahertz?
Yes.
Good design. So you understand it's a good design because 10 gigahertz. Your
See the
schematic-
dx here dx 102 means all 100 picosecond means 1 by 100 is 10 gigahertz. Same will come. It's frequency component. Yeah. Yeah, 101. Means 100 picosecond. It's 1 by 100 picosecond means 10 gigahertz.
So you find that there is a startup time, there is a small delay. Otherwise, the peak-to-peak signal as well as the frequency is same. And that is the, you know that your layout is now freezed